Okay, last time we talked about rate laws. So we know, let's say if we have just a single molecule reacting of something, or one reagent rather, if we have a reaction of A going to B, last time we know that our rate law, aka our rate of consumption, equals K, and then the concentration of A times some exponent. So that's the rate law. But the problem is, it's not so necessarily always that convenient to measure a reaction rate. But what we could do is we can measure the concentration of A. So what we want to do is determine the integrator rate law. And then so if we integrate it, we can then get how the concentration of A changes versus T. So for the purposes of today's lecture, we'll just call it A sub T will be the concentration of A at time T. And then so this one we can measure. So then if we can measure this over the time, we can then get to our final differentiate that and then get back to our rate law. So suppose let's suppose we have x equals 1. This is a first order reaction. So in this case, we know that negative dA dt equals, again, our rate constant times the concentration of A. Right? So this is first order because the exponent on the concentration of A is 1. So in this case, it's going to be relatively straightforward. We move this A to this side, so then we get to dA over A equals negative K dt. And then what we'll do now is we'll integrate. So we'll integrate from some time t to time 0. And then we'll integrate the concentration of A from concentration of A at time t to A sub 0, which is the initial concentration of A. So we know what we're putting in here. So this is known, and time 0 is known. And then so therefore, when we integrate, this should be your known integrals equals negative kt. And then, so finally, then we can then solve for concentration of A at time t. So then we get to AT equals concentration of the initial concentration of A, so A0 times e to the negative kt. So this is the integrator rate law for a first order reaction. Okay, so basically what this means is that you have an exponential fit for first order decay. So if we were to plot versus t, our concentration of A, we would typically see some sort of exponential decay. And then so over here, this is A naught. So one way that people often process this data is if you have some sort of limitation in data fitting. So Excel or MATLAB could fit this just fine, but sometimes if you want to maybe linearize this data, you could take the log of it. And then so if we instead plot, so we still have time axis, but if we instead plot log of A, what we should see is a linearization of our data. And that's because if you look at this formula over here, this is linearized because the log of A at times t equals this constant, so our intercept over here. So this intercept will be log of A naught, and then the slope should be negative kt, or slope rather is equal negative k. So you could fit the data either way, either through the exponential decay or through the linearization of the data. In some linearization doesn't work very well, so sometimes you have to actually fit the exponential. So that's the first order rate law. But one thing I want to point out is there's such a thing as the so-called half-life. So half-life So you might hear this. This is especially common in terms of radioactive decay, which is also first order. So the half-life is when A at time t equals A naught over 2. So in this case, if we plot this, fit this into this equation, so for a first order decay, we'll have 1/2 equals e to the negative kt, and then therefore this is t1/2, so this is our half-life. So t1/2 equals log 2 over k. So for a first order decay, our half-life is natural log of 2 over the rate constant. And so you'll point out that for first order reaction, there's no dependence on concentration. So basically, if you know the half-life, then you can figure out k, or if you know k, you can figure out the half-life. So that's a first order reaction. Yes. So anyway, this is one example of integrated rate law. Let's do a different order. So let me just quickly erase. So let's consider the case where our rate law is in A. So let's say x equals 2. So negative dA dt equals k squared. So this rate law is second order in A. So what this means is that for the reaction to go, we have two molecules of A colliding to form product B. So again, we can integrate. And so we'll have dA over A squared equals negative k dt. And again, we integrate from at 0. And what we should get out is negative 1 over at plus 1 over 0 equals negative kt. And then we'll solve, bring it over to the other side. Oops, negative. And then up here, I'll just bring it up here. And then so we solve for AT equals, oops, I have it somewhere. 1 over okay. So again, if we are looking at our decay plots, so our concentration of A versus time, in this case, we'll have another curve as it decays, and this will not be a good exponential fit. So again, we could try to linearize if you wanted to. So instead, if we plot 1 over A versus time, what we'll see is, again, this 1 over A over time is now a linear equation. So we should be able to see that in this case it goes up. And then our slope is going to be, again, k. And then our intercept over here at t equals 0 should be negative 1 over A naught. OK. Yes. So, but again, I'm going to warn you that linearization doesn't always work very well for all data. So sometimes you have to actually fit this actual equation to get a good fit and get a good back out k and concentration of A naught. So that's second order equation. And then again, if we solve for the half-life, so again, if we substitute A naught, 1/2 A naught for and a sub 0, then solve for our half-life for T1 half, the T1 half for a second order reaction is going to be equal to 1 over K and the initial concentration of A. So for a second order reaction, this T1 half is concentration dependent. Okay, so that's a first order, second order, easy peasy, just integration of a simple reaction. Okay, last example, what if we have a zero order reaction, x equals 0? So our rate is not dependent on any concentrations, so just K. So this is the easiest one. We have equals negative K dt. So basically, this whole thing should be linear, right? So we have AT equals, so easy peasy. So zero order rate law. This is our second order integrated rate law. And so that's how you solve it. So of course, there are often a lot of cases where you're not having just one reagent reacting with itself in first order, second order, zero order. So we'll talk about ways to approach this problem that is more complicated reactions where we have maybe multiple species reacting together and how to solve for the final rate law.